Okay, we meet again. And any questions from this part in the groups and subgroups and other things? Okay, so let us recap what we did last time. So we basically talked about in the last talk. We basically talked about what groups in like more details in definitions, some examples, and then we touched upon some aspects of group. We call, let's say, subgroup, and some properties of subgroups. Not really properties of subgroup that we studied, but we have given basic definition of homomorphism. So this is right here is a separate topic. Homomorphism. Homomorphisms between two groups. Okay, so these are the things. One thing I missed last time. So if the homomorphism was what? Homomorphism is a function from a group to another group. Okay. So it's a function from one group to another group such that the structure that has been given to H and G and H, that structure remains same. So, but by definition, we know that this F does not is not necessarily be injective mapping or a surjective mapping. Okay? So it can be anything. It can be one-to-one or many-to-one, or it can be into mapping or onto mapping. But if this if is a bijection, so if is a homomorphism as well as a bijection. Bijection is purely defined as the mappings, and homomorphism is a function or mapping from a group to a different group. And if it happens to be a bijection, then we call it called isomorphism. That means if it is one-to-one and onto mapping, then it is, and as well as homomorphism, then it's called called an isomorphism. Okay, so that's we elaborated on this homomorphism thing. This is just this extension with the condition that it has to be a bijection. Okay. So then that is done. Let us now move on to slightly complicated structure. So in the groups we had already seen that there is a binary operation, binary structure, some binary structure through the binary operation we have given. Okay. So now let us move to a little bit complicated structure. Complicated structure. We will not touch upon all the different types of structure in mathematics. So we will only be talking about the relevant ones. Okay. So let us say we have a set. Let's call it set A. Let us now consider it is equipped with two binary operations, two different binary operations. Okay. So earlier we were studying one binary operation, and that operation, let's say we used to call it star. In this case, let us say this F, the set, is equipped with two binary operations, such that this plus under plus, it forms commutative loop. Okay, that means under plus operation, the elements of the set satisfy all these three properties, and by commutative I mean that G1 G2 is equal to G2 G1. So this is under plus, this is commutative. And let us say 0 belongs to F is identity element. Of class operation. So since this is a group, okay, so associativity is there, commutative group, so commutativity is there, and under that binary operation I have to have an identity element, okay, since this is a group. And for obvious reason, or as we see in everyday life, in the plus operation, which plays the role of binary identity element? It's the 0 element, because if you add let's say some number with 0, you get the same number, exactly same number. That's why this is like, that is why we have chosen this notation 0 to be the identity element. Now let us take if minus the identity element. This is set minus. That means this set is 0 is removed from this set. This set without the identity element under the binary operation plus. And this dot, this forms again a commutative group. Under dot, okay, under the binary operation dot. So F is a commutative group under the binary operation plus, so it satisfies all these three properties. In additional property is commutativity. If minus 0, so this is set subtraction, so that also forms a commutative group under dot. And let us say that, let's say alpha beta, for all alpha beta gamma belongs to F alpha times beta plus gamma. So what I am doing, I am taking first the addition and then multiply. So after addition, I will get a same element from the set, because this is the group. Then whatever element I get, I multiply alpha with it, and is alpha beta plus alpha. If all these three properties are satisfied, then if all three properties are satisfied, if is said to be a field. So now we actually have familiar structure already. Real number actually satisfies all these properties. Any set of rational numbers actually satisfies all these properties. If you take a real number under binary operation addition, you get another real number. And addition is associative. You can add three numbers without giving any brackets. So that is associativity. Under addition, real numbers are commutative. Identity element is 0, and inverse element for an element, positive element is negative of that. For a negative element, is positive of that. So this is done. And if you remove the 0 element from the real number, let us say, then so that the same is true for the set of rational numbers also. Okay. Now, again, if you see this one, 0 is removed from, let's say, the real number set, then you have associativity, multiplication, under multiplication, usual multiplication. So this is associative, commutative of course, and then identity element here will be 1, and inverse element is 1 over the number. Okay, so that these two things are already satisfied, and this is called the distributive property. So that is, if you multiply one number with a number which is addition of two numbers, it's basically so this multiplication distributes over the addition that we have. So we'll not further go into the details of fields.
Why you are imposing the third alpha dot beta plus gamma?
So this is distributive property. Why I am imposing it? So generally, even the mathematics, we say it in abstract terms, but we generally try to reproduce the real number structure, the complex number structure, the rational numbers, integers. So those are the familiar like sets we will be dealing with in normal day life. So we have to give some structure, some general structure out of these things. And we already know in real number system, we have this distributive property, right? We have the distributive property. Oh, if you don't impose it, it does not come automatically. It does not come automatically. If you think that from these axioms this will come, it will never come.
So here only plus and dot binary operation, and it is possible the suppose plus dot or anything.
Yeah, you can give more structure to it. It does not matter. You give more and more structure.
Then the number third how will be changed?
Oh, that's a pure question of abstract algebra. I mean, whatever you want to change it with, you can change and you come up with your own theorems and all these things.
That would be also called field.
No, that will not be called fit. Fit is precisely this. If you want to add more structure, you define a different structure and name it differently and study the property of it, that's fine. That's up to you. But that will not be called field. If anything satisfies all these things, this is called field.
Field is always defined with two operations.
Yes. Two binary operations. And also another familiar and example is set of complex number. Okay, so all these three fields we are actually very familiar with. Anything else? Let's say set of all the integers, will it form a field? Under usual addition and multiplication operation, that's it. That's it.
No, the multiplication is not common.
In the multiplication, you don't have any inverse element in the integer set. So that's a different structure. Okay, so we'll not be talking about that. That's called ring. So you remove some of the conditions, then we'll have a ring structure. But since we'll not be needing those in this talk series, we'll not be talking about those. And also we'll not further study the properties and theorems of with respect to the field and all these things. But we'll assume the usual properties of, so we mainly will be dealing with real number and complex number, not even rational numbers. Rational number of course is a subset of real number, and we mainly will be like dealing with real numbers and complex numbers as a field element. And so further properties of these fields will be assumed. We'll not be studying the field further. So it's just the definition of field that I wanted to touch on in this series. So it's very simple. So field is basically two binary operations. Okay, so let us write it. So we have two binary operations, f cross f to f dot a cross a to f. Under plus, this is a commutative loop. under dot, this is a commutative group, but without the zero element. Zero element does not have any inverse under the dot operation. And third property is distributive property. So very simple structure. If you know group, you can easily remember these properties and easily can check whether given a field and do binary operation they form a field or not. Okay. So that's it. Now we will be going to a slightly more complicated thing. So we started with what? We started with a set, and then we have started giving structure to it. Okay. So first structure we have given is some binary operation and some properties, and then second structure we have given the take a set and give two binary operations. Now let us say little bit complicated structure. We try to give is, let us say I have a set, let us call it V. Okay, by the way, so these names are basically the first letter alphabet of the corresponding structure that we are giving. So this is a field, so that's why A is usually written as the field. G, for the group, G is usually written as the name of the set. So let us say I have a set and we borrow another set or another structure. So let's say A. So we already have a field and we have another set, okay, V. And let us say we have one binary operation called it a plus, defined over V. So this is a binary operation, plus operation, okay, from V cross V to V. So this is a binary operation over V. And let us say we have another multiplication from the set F cross V to V. So now we slightly differ from the earlier idea from the binary operation. So here this is not a binary operation, we will not call it a binary operation, but this is some kind of a structure. But here it's not Cartesian product of two same sets. Yeah. So here it's Cartesian product of two same sets. That means you give two elements from the same set and give a third element from the same set under this after operating this binary operation. Here what I am saying, you give one element from the field, one element from this set, and I will combine those two and give you a third element from set V. Okay. So this is another structure. So we have plus operation and then field element and another star operation, let's say, but it is not a, strictly speaking, it is not a binary operation from V cross V to V. It is from F to F cross to F. And let us say they follow these following properties. Property 1 is under plus V forms a commutative that means V1 plus V2 is equal to V2 plus V1. Remember, this is an operation defined over V cross V. 2 V1 plus V2 plus V3 and brackets does not matter in this case. exist a minus p, should exist a minus p such that this is c is equal to minus p plus. So under this plus operation, this is a commutative loop. You understand where we are heading to? It's vector space actually we are talking about. And under this star operation, okay, where f is a field, okay, it satisfies these following properties. So under star, actually these are 1, 2, 3, 4. 2, 1 is identity element of the field under this is equal to T. So these properties are defined for all V, V1, V2, V3 belongs to. For all V1, V2, V3 and V, this has to be, these has to be satisfied. Second is, so this is one. So I can take one field element, another vector space element, and we can multiply under this binary operation. And for every element V, if we take the identity element from the field, it should give me the same quantity, same element from V. And then let us say V can define, so let us say we have this binary operation defined, where V is from capital V and beta is from the field. So this will give me another element from V. Which type of object this will be? This will be an object of type capital V. And I can multiply another number to it, another if to it. So this is an object, let us call it a vector, and I can multiply some number to it, some field element to it, and this should be equal to alpha times beta, but this multiplication is defined in if that we talked about earlier. Star third is alpha star V1 plus V2 star V1 plus alpha. And then fourth that we talked about is alpha plus beta. So let us give it a name, and then you will see all these properties, and you can remember all these properties very easily. So this is called a vector space. Okay, usually. So not usually. This is called a vector space. So the elements of this set, let us call them vectors. And this is a field that we already talked about. Field. Let us call the elements from this set as scalars. Okay, now we can easily identify it. So addition of two vectors are commutative, associative. There should be a null vector, okay, for every element. So in the set, in the vector space, and for every element there should be an opposite element such that they nullify each other, gives me the null element. And this actually tells about the compatibility relation between a scalar and a vector. So if you take the identity element from the scalar set, then you should get the same vector. If you multiply the identity element or 1 with vector should give me. And if you multiply a scalar element to the vector and then multiply again another scalar element, you should precisely get the multiplication of of the two scalar element times the vector. And then if you multiply a scalar element with the addition of two vector elements, this should distribute over this. And if you add two scalar elements and then multiply with the vector element, you should get the addition of the individual multiplication with the scalar element with the vectors. And so these properties are satisfied for all alpha belongs to. Yes. So I deliberately mentioned a different sign for plus and star, which is different from the addition multiplication in the field. Usually we don't write in a different notation, but you should remember these are different operations. This plus is defined in the vector space. This star is defined in this operation. Okay. Whereas this plus and this dot were reserved for the binary operations in the field. Okay. Yeah.
Actually, I don't understand the number 2 one. Alpha star, beta star, B.
You don't understand this thing. Why is it needed?
So in the left hand side, alpha star, beta star, B, and in the right hand side, why alpha dot beta?
So that is what I am saying. This is what this is means. The parenthesis has a specific meaning, right? Parenthesis means whatever the expression is, we'll do the operation first inside the parenthesis. Okay, so in this expression, what you are supposed to do is basically first operate these two and get something, and then operate them, then do this operation. Understood? So on the left hand side, what I am saying, you first do the scalar multiplication with a vector. But what will be the result? Is a vector. Then if you want to write scalar multiplication again with the resultant vector, then which operation you are talking about? It's this star operation. That you understood. On the right hand side, what I am saying is a different thing. You first multiply two scalar elements.
Oh, in the field space.
In this field. So field, yeah, this plus and this dot. Now understood, right? So this is, you first multiply the scalars and then multiply the vector or do this star operation. The same thing has been written here. This is a plus in the scale, in the field element. In the field, this operation is defined over the field, but this operation is defined. Actually, yeah, better would be do the parenthesis. So, okay, so all these things, if we cut down into, it basically says if you add vectors, vectors should have these properties, and with the scalar multiplication, scalar multiplied with the vector should have all these properties. Then we'll call V a vector space. If all these properties are satisfied, then V will be called vector space, and usually the elements of V are called vectors, and V is called a vector space. Actually, whenever we say vector space, we have to take a help of another set, another structure which we call field. Okay. So usually that's why usually it is written vector space over which field, that also we have to specify over in this. So in the later part of the talk, when we'll be talking about vector space, we have to give over which field. So usually, as we said earlier, that usually we'll be talking about the real number set, real number field, or complex number field. So it will always be vector space over real or over complex field. Okay. So the elements of capital V are called vectors, and elements of F are called scalars. So whenever, from now on, whenever we talk about vectors, we assume all these properties. Whenever we talk about, let's say, scalars, we assume all the properties of field elements. Then there might be some additional thing depending on which type of structure has been given. So real number has slightly different like properties than complex number. Complex number has much more properties. All these things, those will be assumed. But at least as a basics, at least these properties will be satisfied whenever we will be talking about vector spaces or fields.
So, if we can define the operational multiplication with in the V set, then is there any need for the field? We can define the identity multiplication.
Identity multiplication.
That one star V. That
Sorry.
I'm saying if multiplication is defined with V, then is there any need of F?
This multiplication should satisfy this. How do you define it? I mean, you are giving some operation. So it will be called a vector space over field F. Okay. If you define this multiplication in such a way that that multiplication satisfies all these properties, you are giving, let's say, what you are trying to say, if I understand it correctly, then you by yourself, by hand, you are giving some rule, okay, from A cross B to B. No.
I discussed it. I said it.
No. So you're saying, what is the need for it?
I'm saying why we need to define vector space over a field.
Why do we need to define?
Why do we need always a field to define a vector space?
Only vector space, how will you define it? I don't know.
Where will be the problem? Where will I get stuck?
No, vector space, of course, see, this is a structure that we are trying to come up with. And of course, in our mind, the thing that we want to explain are basically vectors. So we already have physical vectors, we know all the properties of the vectors. And from there, we try to come up with some general definition such that our usual vectors in 2D, 3D, in physics and wherever we want to study satisfy all these things. But it will be little more general. That's the idea of abstract algebra. So you basically, in everyday life, you have some objects or some set, some element, and you try to come up with some general definition so that you can explain those as well as you can go to a much more different structure and all these things. So now, let's say even in the case of our normal vectors, okay, let's take that as an example. Okay, let us say we consider all the vectors, or let us not call them as vectors as of now. Let us say.
Procedure. You have defined the element of the scalar is always element of the field is always scalar or anything.
Sorry.
Element of the field is always scalar or
Element of the field. The elements will be called as scalars.
always. That is the
Yeah, whatever the element in the field, we'll call it a scalar. We'll name it in that way. It's not a derived property. It's a definition that we'll be calling the elements of the field to be scalars. Whenever in the context of vector space, it is always defined over a field, and whenever the element of the field, whenever we'll be taking the elements from a field, we'll be calling it as scalars, and we precisely know the properties of those scalars. At least some of the, very basic properties that they have to satisfy at least, and then it might have additional things. Okay, so let's take that as an example. Okay, so let us say I have a special point. Okay, call it O. Then let us say, so what are vectors? Let's not call it as of now. Let's not call it vector. We'll say we take, let us say, a set, okay, and we take all the arrows that we can draw from this, let's say in 2D. We are working in 2D. Okay, so on the board, all the arrows that we can draw. So in principle, it can go over the board up to infinity. Since this board is limited, we cannot probably draw it, but you can imagine. Okay. So let us say all this. So let us take a set B to be collection of all these arrows as well as the spatial point all the arrows starting from O and the point O itself. Right? Now we said already that it has to have a binary operation. So given two arrows, we have to give a structure so that we can add these. That is the rule that you have to specify. Okay. Let us say the addition of two arrows, some color chalk. Okay, fine. Addition is defined to be, right? If you have V1 and V2, we define it that addition to be, you take the parallel line from the endpoint of V2 and parallel to V2 from the endpoint of V1. Now you understand where we are heading. So this is my, let's say, the binary operation I came up with, or we came up with. Now let us check. So addition is defined in this way. Of course, we not only have arrows, we have one more extra thing, that addition has to be also has to be defined. Let us say that definition is simple. So between two arrows, arrow plus some arrow is basically, let us say, is parallelogram. And let us say arrow plus the point O is the same arrow. That is defined in this way, and this special point O addition structure is the same arrow itself. So then we can check that this is actually, if we define in this way, then this is actually a commutative group under this binary operation. The first four properties are satisfied. Okay, associativity will be little bit like lengthy to prove but you can say that is satisfied. So of course you see the commutativity is already there, right? So parallel, you take this first or that first, does not matter. If V1 plus V2 or V2 plus V1 are the same. Associativity, you have to put a little extra effort to prove that. Identity element, of course we have given a special element and special operation, so that already will satisfy the identity element. And under the same law, you see that if we draw a same length arrow on the opposite side, they will cancel and give me the point. So those are the things. Now comes the question, why do we need fields? So these are some bunch of points. Now, another thing we have in the vectors is scaling,
Scaling.
right?
Yeah.
So in order to define those scalings, you need to come up with some operation with the scalars.
Yeah.
But the scaling is already there in the vector.
No,
No,
scaling is not.
without field. Actually, either I have
Where-
to extend the space or I have to add the field. It is something like that, no?
Like you need to extend
No,
the
no.
space.
Say, if I want to define scaling without a field, I can do it via direct product. I will say there is
How do you
a
define?
element, others are 0 and there is a vector. So,
No, I don't understand. How do you do the direct product?
the whole vector will be multiplied by each of the elements. So the dimension will be increased at the last stage.
Whole vector will be.
Say the dimension is 2 plus 1 and I am trying to define
We did
scaling.
not even come up with any dimension here. We don't have any dimension. You have to define vectors or vector space. You don't need any dimension. Until now, we have one binary operation, which is a commutative group. So now, if you stop there, it's just a group, normal group. Then we don't have to give any structure, any additional structure. You can, if you only stick to this, then you might as well study groups.
But inside V you cannot define a multiplication kind of thing without field.
In the vectors, we don't have multiplications, right? In general, do we have?
The dot product and everything is through field. You're saying.
Dot product is what? After dotting two vectors, you are not getting any vectors.
Scalar.
You are getting a scalar. So that is already gone. Cross product is there, but that is a very special case of three dimensions. So you cannot go further with that. You cannot even define cross product in 2 dimensions. Of course, we are not talking about dimensions yet, but let's say if we define it this way on this line itself, sorry, on the plane in a plane, then you can always define the vector space in this way, and all these things will be done. But you cannot define the cross product and all these things here. Right? Cross product, of course, gives 2 vectors, and so you get 2 vectors, gives another vector. That is there, but that is a very, very special case of 3 dimensions. Okay, so now you are kind of not stuck. You can stop here, but then what's the need of defining vector space as a different entity? You might as well club this into a group and study the properties of group. Okay, so now since we try to come up with some general structure from our daily life we see, one of the thing we see is that actually is vector. So then you know that you can scale a vector. So now the scaling is basically multiplying by a number. So then you come up with, okay, so we should not stop here. we can go a little bit further, give a little bit complicated structure. Let us say we want to scale these vectors with some numbers. So now let's go to little bit general case. We'll not call it a number, let us say we'll call it a field element, and we want to scale them appropriately with the field element. And those are those four axioms. And now you can see that if this f is let's say our real number, then all those four properties are satisfied in this set with the following operations if we specify. Let us say if we specify that when we take identity element from the real number, we don't scale at all. A scale by one unit is basic elements, we remain the same. Okay, that the structure you are putting into it, and scaling by some number means the length of the arrow is increased or decreased by that number. Okay, appropriately. Okay, and then if you say I scale by one unit, one number, and scale by another number, then total length final will be the scaling by the multiplication of those two scalar numbers. And if I add two vectors and then scale it, then it's equivalent to scale the resultant vector with the same number. And if we specify, yes, so addition and then scaling, and the other is, so if you can see that we scale by one number, then scale by another number of the same vector, and then add, should be equal to just add the two numbers, scalar numbers, and then scale it. Okay, so these are four things that we have to give by hand. And of course, you might wonder why this is there. It's probably not needed, but actually we have to give it by hand, otherwise it's not automatic from the other examples. Okay. But yeah, once you give it, so there are different conventions. Usually this is taken, but there are slightly different conventions that you give this as the axiom, and then this is automatic. Okay. So if you give this structure, then some of the properties are automatic. What are those properties? One is 0 times, if you scale by the 0 element from the field to the vector, it will give you the null vector. So this is, now let us put arrow on top of the vectors. So 0 times v should give me null vector. This is property 1. Property 2, minus 1 times v should be equal to minus. So take any vector, multiply it with the minus 1 element of the field, you should get the inverse of the vector. So these are two properties that those are followed from these axioms. These has to be satisfied, otherwise we also cannot do much of the things. Okay, so these are the things. So of course one example is this, and let us come to another slightly interesting example. So vector space always defined over field F. So we have to have, first we have to have a field, and then only we can define vector space. And as we see, that was example 1. Let us take this as an example 2. So we already said that V cross V has to go to V. And star these two are defined. Let us replace V by F and class by class and star by. What does it mean? Let us replace V by capital F and this plus operation by the plus operation of the field and star operation by dot operation. So that means we are talking about if times if and dot if times if. If you replace V by the field F and plus operation, this plus operation by plus operation and star operation, this star operation by dot operation, then you can easily check that all those 8 properties of vector space will be satisfied. First 4 are already satisfied, but because plus is a commutative group in the field itself, so this first 4 are already satisfied. Right? What were the last 4? 1 star B should be V, alpha star beta star B should be equal to alpha dot beta star B. Alpha star 1 plus 2 should be equal to alpha star B1. These were the 4 properties. Now we say that this vector element, we replace it by scalar element, and the operation are replaced appropriately. Okay. So now instead of some V, I write it, let's say some alpha here. And since this is alpha now, so this star is replaced by dot. Similarly, this V, I replace it by, let's say, gamma here, gamma here. So this is replaced by dot. These are replaced by dot. Okay. So let us say this is beta, V2 is replaced by gamma, V1 is replaced by beta, and V2 is replaced by gamma. Then these are replaced by dot, these are replaced by normal plus, these are replaced by dot, these are replaced by normal plus. And you see that these are already satisfied with the field definition itself. Lost. So what we say, that we take a different set which we call vector space and which has some connection with the field. Now what we are saying, that this different set, let us take it to be the field itself and try to see whether this field itself satisfies all these vector space properties or not. And we saw that if we replace V by F under this operation, under the plus operation, we can replace this plus operation by the usual plus operation in the field in it. And the star operation, now we don't need a different star operation. We can replace it with the dot operation in the multiplication operation that was there in the field. Right? And first 4 properties of vector space is already satisfied in this operation itself. And for the second operation, okay, for the last 4 properties of the vector space are automatic in the field. These are automatic in the field. This last four, this one, and what was the fourth operation? Fourth was alpha plus beta star b. Now we replace it by someone is equal to alpha dot sum. This was not there in the field definition, but since multiplication is commutative, so we can swap this gamma around and come up with this. Okay. So field actually by itself satisfies all the properties of the vector space. So a field is always a vector space over the same field. So from this example too, we can say if is a vector space over field. Okay. So this is our example 2. 36. Okay. And maybe this is a good point to stop with example 2. So two important examples we saw. Let's say all the arrows from a given special point on a plane actually satisfies all the properties of vector space given the addition operation is the parallelogram law and the scalings are usual scalings with respect to a number. And another important example that we saw, that given a field element, the field by itself satisfies all the properties of the vector space under usual plus and dot operation, under usual plus and addition and multiplication operations. Okay, so field is a vector space over the same field itself. Okay, so let us stop here with these examples. If you want to see some other examples, we'll maybe we'll maybe discuss some examples in the next class, and then we'll go to the definition of basis, subspaces,